Good afternoon, sir. This is topic about the basics of damage stability determination in relation to SOLAS chapter 2 and 1 criteria in damage stability. Basics of damage stability determination in relation to SOLAS chapter 2 and 1. Damage stability is the study of vessel stability to remain afloat and stable after sustaining damage that causing flooding of one or more watertight compartments. The International Convention for the Safety of Life at Sea, SOLAS Chapter 2 and 1, establishes criteria to ensure that ships have sufficient stability to survive specific damage scenarios. Their requirements aim to enhance the safety of ships, their crews, and passengers. Key principles of damage ship stability. Number 1. Watertight integrity and subdivision. Ships are designed with watertight bulkheads and compartments to limit the extent of flooding in case of damage. The subdivision of the ship into watertight compartments ensures that the vessels can remain afloat and stable even if certain compartments are breached. Number 2. Floatable length. The floatable length is the maximum length of the ship that can be floated without causing the vessel to sink or lose stability. The positioning of watertight bulkheads is determined based on floatable length calculations. Number 3. Stability after damage. The ship must maintain sufficient positive stability measured by the metacentric height GM and rating lever G after flooding. SOLAS Chapter 2 and 1K criteria for damage stability. Number 1. Applicability. The damage stability requirements under SOLAS Chapter 2 and 1 apply to passenger ships, AG, ferries, cruise ships, cargo ships over 80 meters in length. Specific additional criteria for tankers and vessels carrying hazardous cargo. Number 2. Subdivision Index passenger ships. The Subdivision Index A measures the ship's stability to survive damage. It is calculated based on probabilistic damage stability principles considering and probability of damage PY or PI, likelihood of damage occurring in different compartments, probability of survive SI, ship stability to survive damage to those compartments. Weighting factor VI, number of passengers exposed to risk. The vessels must achieve a minimum required index A, which is specific to its type and size. 3. Extent of damage. SOLAS specifies the extent of damage that the ship must withstand, including horizontal extent, damage to the hull over a length equal to L20 minimum 3 meters. Vertical extent, damage from the baseline up to the bulkhead deck. Penetration depth, damage extending inboard by a specific distance, usually B5, where B is the breadth of the vessel. Number 4. Damage assumptions, symmetrical and asymmetrical flooding. Stability is assessed for both symmetrical and asymmetrical flooding cases, as flooding may be uneven depending on the damage location. Permeability assumptions. Different permeabilities are assumed from for flooded species based on their uses. 95% for machinery spaces, 60% for cargo holds, 85% for passenger spaces. Number 5. Stability criteria. After damage, the vessels must meet specific stability requirements. Number 1. Residual rating level G. Minimum residual GG of 0.05 meters at an angle flooding. Number 2. Range of positive stability. The range of positive stability after flooding must be at the least 15 squared angle of hill. Angle of hill. The hill angle after flooding must not excess 25, ensuring operational safety for passenger and crew. Area under the rating curve. The area under the rating curve must meet prescribed minimum values to ensure adequate instability. Damage stability calculation methods. Number 1. Probabilistic approach. Based on the likelihood of damage to various compartments and the ship's ability to survive, commonly used for passenger and large cargo ship. Number 2. Deterministic approach assumes specific worst case damage scenarios and evaluates the ship's ability after flooding. Common for tankers and smaller cargo ships. Modern stability software. Stability software perform rapid calculations for damage stability, accounting for free surface effects and flooded compartments, asymmetrical flooding scenarios, structural stresses, and residual stability. Critical factor influencing damage stability. Number 1. Free surface effect. Loaded compartments introduce free surface moments, reducing metacentric height, GM, and stability. Number 2. Progressive flooding. Opening or failures in watertight boundaries can lead to flooding upgrading to adjacent compartments. Number 3. Ship loading condition. Initial loading conditions, e.g. cargo distribution, ballast, significantly influence the vessel's response to loading. Number 4. Design features. Features like double bottoms, longitudinal blockades, and flood control arrangements enhance survivability. Features to enhance damage stability. Number 1. Watertight integrity. Regularly measurements of watertight doors, bulkheads, and hatches. Number 2. Damage control plans. Detailed plans and drill to manage loading and maintain stability. Number 3. Baffle plates. Pitting baffles in the tanks reduce the free surface effect during flooding. Number 4. Cross-flooding arrangements. System that balance water ingress between compartments to minimize healing. Number 5. Use of balance. Adjusting balance to improve stability during emergencies. Thank you.